Hi, my name is Vicky Kaspi, and it is a tremendous honor to have been awarded the Bakerian Medal. And it's a great privilege to give this lecture and describe to you my current research, which is on fast radio bursts, a new cosmic phenomenon of unknown origin. So fast radio bursts. What are these? So first of all, the short answer is we don't know what they are. And when people ask me what my current research is on, I sometimes say, I'm not really sure. And this cover of Nature very eloquently conveys that these are mystery objects. And so let me explain to you what fast radio bursts are. First of all, it's a public talk, and I want to be sure we're all on the same page. When I say the word radio, some of you of a certain generation will remember this device, which uses an antenna to collect radio waves that are being transmitted through the air. The radio waves induce currents, which are amplified in the electronics inside this radio device, and then later converted to sound using a speaker. But it's really radio waves that later get converted to sound waves. And you see there's a dial here that lets you adjust probably the volume that's changing the amplitude or the amplification. But also there's a dial that lets you change frequencies so that you can tune into your favorite radio station. When you tune it, you really just pick out one or two radio frequencies or very narrow, or one radio frequency, very narrow range where your radio station happens to be transmitting, and you neglect all the other radio waves. But just to be clear, radio waves are not at all sound waves. It's a common misconception. Radio waves is electromagnetic radiation, just like the light that your eyes can see are electromagnetic waves. But radio is a much longer wavelength than the optical range. And that's the regime that we're in. So we're collecting here radio waves from the cosmos using antennas, just like on that device, but slightly more sensitive antennas that can see across the universe. And here's an example of a radio telescope. You can see the Parkes Radio Telescope in Australia. There's a 3-story building under this giant reflecting dish. So you see the scale of the telescope at 64 meters in aperture. And the radio waves come from the cosmos and strike the parabolic dish and get reflected to a focus where there's an antenna in this focus cabin up here. And so that's how radio telescopes work. Inside the focus cabin, the antennas, currents get sent down to a control room where they're amplified and digitized and recorded via computers. And so what this radio telescope does when it's detecting these mysterious fast radio bursts is it's constantly collecting data and occasionally detects a short burst, a burst that lasts only a few milliseconds or a few thousandths of a second, and then goes away. Now, these bursts, you don't know when or where they're going to happen. That's why they were so hard to discover. And the first one was only reported in 2007. And even then, people were a little skeptical that this wasn't some sort of terrestrial signal, something not astrophysical. But today we know this is definitely astrophysical. And it's not rare, it's very common. We think that if you could observe the whole sky all day, you would detect on the order of 1,000 fast radio bursts every 24-hour period. So there's something in the universe that's creating these and creating them ubiquitously. But as of today, their origin is unknown. We don't know where we don't know what sources are creating them. Although we do have some ideas, and I'll be describing those to you in this talk. Now, how do we see a fast radio burst? Where those radio waves that are collected by the dish and digitized and recorded on computer, we can display it like this. Since our eyes can't see these bursts, we don't see radio waves. we can display it in a plot. We call this a waterfall plot because it looks like sort of like water, I suppose. And here what you can see on the x-axis is time, and this is a total of about half a second or 500 milliseconds. And this is radio frequency on the y-axis. So here the antenna on the Parkes telescope was sensitive from a range of about 1.2 gigahertz till just over 1.5 gigahertz. And it can see all the radio stations or all the radio band at the same time. So unlike the device that we use to detect radio waves that are terrestrial to listen to your favorite song, here we don't just detect one frequency, we detect many frequencies at the same time because nature provides all those frequencies. We want to be able to detect a wide bandwidth of radio waves. In fact, you can see here something that's clearly terrestrial, not cosmic. That's the horizontal black line that's at a fixed narrow frequency and is on persistently. The astrophysical signal, the fast radio burst, is this line sweeping through the band, and we call it the Lorimer burst because it was Lorimer et al. Who first, Dunk Lorimer, astrophysicist colleague and friend of mine, who led the team that first detected this. And notice that the burst arrives first. It arrives earliest at high radio frequency, and then it sweeps through the band and arrives later at low radio frequency. And I'm going to assert that that is a signal that it's coming from far outside our Milky Way galaxy. And I'll have to justify that to you, and I will shortly. But if in the computer, in software, you correct that delay, because we believe the source produces all the radio frequencies at the same time, if you correct it to what you would observe if you were right next to the source, because we think it's a propagation effect, the travel through the interstellar and intergalactic mediums that produce this delay. If you correct it, you get this inset here, where here we've just delayed all the lower frequencies, or rather delayed the higher frequencies or retarded the lower frequencies, either way you want to think about it, and then combine all of the radio frequencies together. And here's what you see. You see absolutely nothing to begin with, just the static in the radio receiver, a sudden burst that's extremely bright, and then it goes away and it does not come back. So that's a typical fast radio burst. Now, when I say it's coming from far outside our Milky Way galaxy, I want to be sure we're all on the same page. This is not the Milky Way galaxy, as you can be certain, because it's hard to take a picture of the outside of your house when you're sitting in it. So we're inside the Milky Way galaxy, but this is a galaxy that's not unlike the Milky Way. And if it were the Milky Way, we're sitting about over here relative to the center, sort of on the outskirts of the galaxy. And I'm asserting that fast radio bursts come from far outside the confines of our galaxy, in fact, from clear across the universe. Yeah, you were here. And so just to be sure we understand the scale of the universe, let me use this wonderful graphic that I got from Wikipedia. Here's, you're familiar with the Earth as a planet and presumably as a solar system. And here we've zoomed out so that the Earth is now indicated in that little red splotch over there that's pointing to the Earth. And here's the solar system with the sun at the center. But if you zoom out by a similar amount, you see now the solar system is basically a dot in the interstellar neighborhood, and you can see the nearest stars inside our galaxy. So really, the solar system is tiny on the scale of the nearest stars. And then if you zoom out even further to the full scale of the Milky Way galaxy, the interstellar neighborhood is now just a dot on the outskirts of the galaxy. But you can zoom out further to the local galactic group, and now you can see the Milky Way, again in red, is just a little smudge in the scale when you can see the full group, local group of galaxies. You can see the Andromeda galaxy over here, which is a nice, practically naked eye object on a clear night from the right location. But if you zoom out of the local galactic group, again, by a similar factor, you can see the whole galactic group is now just a smudge in the Virgo supercluster of galaxies. So each of these smudges is a whole group of galaxies. And you can zoom out even further so that the entire supercluster here is now just a smudge among smudges of other superclusters of galaxies. And if you zoom out to the largest scales of the universe, we're talking here billions of light years, to the entire observable universe, the local superclusters are now just a single smudge. And this is the scale on which I am claiming fast radio bursts are produced and are arriving, or the bulk of them. So from the largest scales of the universe, that's where these bursts of radio waves are coming from. How do I know that? Well, I'm going to remind you of a phenomenon. I said that the radio waves were dispersed through that radio band. And that dispersion is very similar to a phenomenon that everybody's familiar with. That is that white light is made up of the color of the rainbows. That is, when you shine a beam of white light through a dispersing object, like a prism, it disperses the components of that white light into many different colors, the colors of the rainbow. And it's the same reason that the rainbow is produced. Basically, in this case, sunlight is dispersed by water droplets that are in the air into the constituent colors. So the different colors not only get spread out by the dispersive medium, the glass or water, it spreads them out geometrically because they get spread by slightly different amounts depending on their frequencies, depending on the color. It's also true that the different colors travel at slightly different speeds in those media. So if you could shine a pulse of white light, you would see the different colors come out of the prism also at slightly different times, both at different angles and at different times. And so that is what we mean by dispersion. Now, when radio waves travel through space, they're dispersed. And you might say, well, space is a vacuum. What could possibly disperse the radio waves? It's not like glass or water. But in fact, space is not a vacuum. And there are free electrons everywhere, including in our galaxy. And so it's the free electrons that I'm referring to here that disperse radio waves. So space is definitely not a vacuum. There's all sorts of stuff there. There's dust, there's gas, there's molecules, there's lots of material there. It's not very dense because it is space, so it's very dilute. You would not be able to breathe there. But in particular, there's the free electrons, and those really matter because what they do to radio waves, here's a nice video that's going to show you a fast radio burst source producing a burst of radio waves. What you'll see is that the free electrons that are not shown so obviously in this movie, they will disperse those radio waves into their constituent frequencies, which will represent with colors because we can't show radio waves. Our eyes can't see them. So there's the FRB source that starts out like white light, all the colors together. And as it travels through the interstellar and intergalactic plasma, that is the encountering ionized gas and free electrons, it arrives at Earth, at an earthbound telescope, in this case, CHIME, as I'll describe later, in terms at different times, depending on the frequency. I'll show the movie one more time. All the frequencies are produced at the source together like white light. But by the time it gets to Earth, those colors have been dispersed by free electrons in the interstellar and intergalactic media. Now, if this were the galaxy, we actually have nice maps of our galaxy in terms of the density of free electrons. So we know this is a map here showing or it's a model showing the distribution of free electrons in our galaxy. And so what that means is that when a radio burst travels through our galaxy, it gets dispersed by these electrons by an amount that depends on the direction from which it's arriving. So that if it's nearby, you'll see less dispersion because it travels through fewer electrons. And if it's far, you'll see more dispersion because it travels through more electrons. And there's some directions where if it came from, it wouldn't encounter many electrons, even though if it's far away. That's why you need to know the distribution. And you can, this is perhaps a little technical, but I think if you're understanding, and I'm emphasizing this for good reason, because if I'm going to claim to you that fast radio bursts are cosmological, coming from cosmological distances, I'm trying to justify that to you. This is now a contour plot where the galactic center is at this plus sign here, and the Earth is in this sort of Pac-Man-like region over here, and here are spiral arms. This is a model that shows you contours of constant free electron column depth. So the total number of free electrons anywhere on this contour, if looking from the Earth, is a constant. And so using a model like this, when we detect the dispersion of a fast radio burst, when we see how much it's dispersed when we detect it, we can compare with what's in the free electron distribution model and learn how far away it is. So if it comes from this direction and it has an amount of dispersion that's consistent with this contour, then we know, oh, it's this distance away. You can just use the map to determine the distance. And in particular, for the Milky Way galaxy, in any direction, there's some maximum amount of dispersion that the galactic electron content can explain. At some point, the galaxy runs out of electrons. And so as you leave the galaxy, the total number of galactic free electrons that are available for dispersion runs out. So there's some galactic maximum, and that's key. So we determine the distance by using the dispersion measure. And here's just for the aficionados comfortable with equations, it's basically the time delay between two different radio frequencies is an inverse square law. So this is actually not exactly a line, it's a parabola. But the point is, coming back to the Lorimer burst, this dispersion, so the degree of dispersion, which is proportional to this quantity called the dispersion measure, which itself is, as I said, proportional to the total column depth of free electrons, or the total number of electrons between us and the source. You can measure that. And we know for this direction on the sky, due to the Milky Way, the maximum dispersion measure that can be accounted for in our models is about 25 in arcane units. Don't worry about that. Whereas what we measure here is a dispersion measure of 375. So 10 times, over 10 times higher dispersion than can possibly be explained by our galaxy. So that was an immediate signal that this object has to be coming from far outside our galaxy. And if a radio bursting source is located far, far outside our galaxy, I've shown you the distances involved. If you can detect something this bright from so far away, that implies it must be very, very bright intrinsically. It must be quite an explosion for us to be able to detect those radio waves from clear outside the galaxy. And that's why astronomers got very excited by this and started asking questions like, well, what could these be? Some huge explosion of radio waves that only lasts a few milliseconds. It has to be something very compact and something extremely powerful. And so the sorts of hypotheses that were suggested, which, by the way, the number of theories for a long time outnumbered the number of fast radio bursts we had yet detected. That was for a few years. These hypotheses included exploding stars like supernovae, or colliding neutron stars. We needed neutron stars. That's a very compact sort of object, something I actually used to work on an awful lot and still might. I don't know if I do or not. And if you collide them, you might get a radio burst, or perhaps a neutron star colliding with a black hole. Or perhaps comets or asteroids impacting neutron stars, or evaporating black holes. The models went on and on. Always having to produce something very short, so requiring a compact object. That's why black holes sometimes got invoked. I've highlighted one of the models with a word. It's a word that you might not have heard of, magnetars. And I'll explain what magnetars are, because those are presently a leading model for explaining fast radio bursts. So many different models were suggested, but as I'll explain, magnetars seem to be the best model currently, although it's definitely not certain that all fast radio bursts are magnetars. So what are magnetars? So magnetars are ultra highly magnetized neutron stars, and neutron stars are extremely dense stars. A teaspoonful weighs 1 billion tons. These are remnants of the collapsed cores of massive stars. So neutron stars exist. We know them. We know of thousands of them in our galaxy. And we know they have high magnetic fields. And in some cases, these neutron stars, their magnetic fields render them extremely unstable to some sort of catastrophe on the star. I shouldn't say catastrophe because the star recovers. So some sort of massive explosion, either crust cracking or some sort of magnetic event involving magnetic reconnection. So we see we've observed these explosions, particularly in X-rays and gamma rays. That's something ubiquitous. It's something actually my research group worked on for, 20 years. In any case, we know magnetars exist, and they have within them a huge magnetic energy reservoir. So we've seen that reservoir gets tapped and yields large explosions like the one in the cartoon here that we detect with X-ray and gamma ray telescopes. But magnetars have not been known for large radio bursts. So you might say, well, if you know of magnetars, they don't produce large radio bursts, then why do you suspect they could be fast radio bursts? And the argument is just that because they're neutron stars, they're collapsed objects, they could produce short bursts, and the energy is there to produce a very intense, the very high luminosity burst that is implied by their large distances. So could magnetars explain FRBs? Perhaps, and I'll talk more about that later in the talk. Now, you might say, well, why can't you just go and when you detect an FRB, look and see what galaxy it came from and, learn so much about from where it is in that galaxy? Is it a region you'd find magnetars, or is it in some other region? What types of galaxies are these associated with? The problem is that radio telescopes do not localize very well. In other words, the uncertainty region when you detect a fast radio burst using a telescope like Parkes is very large. So in other words, radio telescopes don't have very good angular resolution. And so if you look in the region from where Parkes can say with certainty that the source arrived, there's probably 1,000 galaxies there. So there's no way to identify the correct galaxy. On the other hand, you can go to a larger aperture telescope that is a larger reflector, and that will reduce the uncertainty region. But even with one of the largest radio telescopes on Earth, the Arecibo telescope in Puerto Rico, which actually ceased functioning fairly recently. But even then, with the largest apertures we've been able to build on Earth, you cannot pinpoint with sufficient precision the location on the sky from which the FRB originated. However, there's a different type of radio telescope called a radio interferometer, like the Very Large Array, as I'm going to explain to you, which actually does let you pinpoint things very well and would allow you to come up with an error region if you could detect an FRB with the interferometer. The problem is the interferometers can't see a large area of sky. And since this is a transient phenomenon, you don't know where to look. And so you could stare and detect nothing for years with the interferometer. That's the problem. And if FRBs, they burst once, you miss it, well, you have a problem. But here's the Arecibo telescope as it was before it suffered a truly catastrophic event, as you can Google if you're interested. This is a 300-meter reflector. This is a 3-story visitor center here and parking lot. Very, very large structure. This is actually me at the top, right over here where this is a catwalk. At the top of the catwalk, we were standing right there, me and a couple of colleagues. If you zoom in, you'll see my knuckles are white because it is very scary up there. And in fact, you might be familiar with Arecibo because it's appeared in some popular movies like James Bond GoldenEye. starring Pierce Brosnan. And incidentally, if you watch that movie, you'll see Pierce Brosnan was running on that catwalk. Actually, sorry, it was James Bond running on the catwalk. It was not Pierce Brosnan. It was his stunt double, because he was didn't really want to, wasn't too excited to run on that catwalk. So I'm very proud to say that I have done things that James Bond was too afraid to do. But in any case, I'm mentioning Arecibo to you because Arecibo detected a very interesting fast radio burst back in 2016. And here you can see the telltale dispersion sweep and the sum of all the frequencies post de-dispersion here in the inset, nice radio burst. And the reason this was so exciting is because we realized that it was repeating. So I mentioned to you that the Lorimer burst came and went and was never seen again. That's still true. And that was true until the Arecibo FRB was discovered. No other FRB had been discovered to be repeating at the time. And so when we found 10 repeats from it, we were incredibly excited and we got quite a bit of press. It was actually PhD student Paul Schultz at the time who made this wonderful discovery. You could see all the different press that we got from it. But what was really super exciting is, number one, it told you it could not be an exploding star that destroys itself. I mean, in one plot, we knew that we had eliminated a whole class of models for FRBs, because anything that's colliding neutron stars, they can't collide 10 times. It doesn't work. And so that was exciting, but also it offered us an opportunity to go to an interferometer, ask for time and say, we can stare at the sky and we're guaranteed if we wait to detect something. And so we went to the Jansky Very Large Array in New Mexico, this interferometric array of radio dishes. And we observed for 60 hours and detected nothing. And 60 hours of VLA time is not easy to get. So that was pretty frustrating. But we begged for more time and they gave us more time. And in the test observations of the next observation, boom, we got a burst. You can see here, this is the position on the sky. For arcane reasons, the VLA image comes out like a series of lines that all converge to a point where the source is. And that lies within these black circles, which were the error regions, the uncertainty regions from the Arecibo telescope. So that was super exciting because that immediately pinpointed the location for the first time of a fast radio burst. And we knew it was the source because it suffered the same amount of dispersion as the Arecibo source did. So it was both in the same sky location with the exact same dispersion measure. There's no question. And since that time, we've detected this event hundreds of times with many different telescopes. So it's clearly astrophysical source. And it then allowed us to go to an optical telescope, the 8-meter Gemini Telescope in Hawaii, and look, and we were expecting to see a nice big galaxy there. And instead, this is the optical image that we saw. It was just this tiny little dwarf galaxy. And so this is, sort of a twist and turn in the story. That was a big, our jaws sort of dropped when we saw that. We were not expecting this fast radio burst to come in a dwarf galaxy. Most stars are not in dwarf galaxies, or the most of the light that we see comes from large galaxies. So why would it come from dwarf galaxy? But the good news was that the dwarf galaxy, we could measure the distance, and it definitely implied the cosmological distance that I advertised at the start. So everything that we had inferred indirectly from dispersion measure, we knew was correct because of the because the dwarf galaxy was indeed at a cosmological distance. So that was also a nice confirmation of everything that we thought we understood. But since that time, there have been 12 more fast radio burst host galaxies identified through this localization method with a different interferometer located in Australia, the ASCAP collaboration. Here's a sample where you could see the white circle represents the uncertainty region of the fast radio burst that they detected, and the different host galaxies as a whole. Diversity of them. They're not all in dwarf galaxies. You can see this one's in a lovely spiral. So that sort of told us that, the Arecibo repeater was that dwarf galaxy representative? And you might say, well, no, It's not representative because these are all large galaxies, but all of these ASCAP sources are not repeating sources. ASCAP is able to both find and localize fast radio bursts. And so because they can detect fast radio bursts with a feed array that allows them to see large area of the sky. So that gives them the opportunity to both discover and localize immediately. But none of these were repeating sources. Repeaters still at the, there was just that lone repeater until recently, as I'm going to explain. So in 2019, where did we stand? We knew of one fast radio burst that repeated, which ruled out exploding or colliding stars for that source and enabled the first FRB localization. But it left many open questions. Specifically, do all FRBs repeat? And you just have to wait a long time? Because that maybe there's two classes of FRBs. Maybe some are exploding stars and some are something else. What is the nature of the bursting source and why is it in a tiny galaxy? And what we knew we had to do was find more. Because just there's one or two, when you have a diversity of phenomena, when you have some repeat, some don't repeat, some are in dwarf galaxies, some are not, you need statistics to be able to solve the mystery. So you need to find many of these objects. And now I turn to the last part of the talk, which is about the new radio telescope that we've built in Canada called CHIME, which stands for Canadian Hydrogen Intensity Mapping Experiment, which tells you that actually this telescope, and yes, you're looking at a radio telescope here, a very unusual design, was designed for cosmological purposes. And we later turned it into a wonderful fast radio burst detector, as I'll explain. So this is located in Penticton, British Columbia, at the Canadian National Research Council's Dominion Radio Astrophysical Observatory. And it consists of 4 cylinders, reflecting cylinders. So we don't use a dish, we use cylinders that reflect only in one direction. Each one is 20 meters by 100 meters. So it's a very large structure here. It's the area of, in Canadian units, 5 hockey arenas. It's a transit telescope, so it has no moving parts. You can't steer it. You can only look at directly what's overhead. And it's oriented exactly north-south, so that the sky, any source rises in the east, transits overhead, and sets in the west. So in that way, we can see the full northern sky every single day, the whole northern sky. It's sensitive in a wide range of radio frequencies, 400 to 800 megahertz. And the way it works is that on the axis of each of these 4 cylinders, there's hanging 256 antennas. And so the radio waves come in, reflect into the antennas, which are they're connected by cables and amplified and digitized extremely rapid. So you have 1,024 antennas now. It's like having 1,000 Parkes telescopes all operating at the same time. The input data rate here is 13 terabytes per second, which is comparable to the world's cellular network, the full world's cellular network. So it's a massive amount of data that is being collected and processed in real time, thanks to an incredibly powerful correlator. This was funded by the Canadian Foundation for Innovation and is a collaboration of many institutions. Here's just 3 of them, and I'll list the others later. This is the CHIME fast radio burst team standing the axis of one of the cylinders. Now you might wonder why cylinders. So in a conventional radio telescope like Parkes, it has a field of view that is circular, but pretty small. So if you want to study a transient phenomenon, you have to get super lucky because most of the events on the sky you miss because that's the only region you can see. You have to look for a very long time and get lucky. But with a cylinder, you only focus in one dimension. And so you can actually see an enormous swath of the sky all at the same time. And that is fantastic for transients because, in contrast to the small field of view that is enabled by the Parkes telescope, you have a much several orders of magnitude larger field of view. And then as the sky transits overhead, you have a much greater probability of detecting a transient event. Doesn't mean you won't detect all of them, but you detect many more using CHIME. And so that was why CHIME has been able to be very successful in detecting fast radio bursts. And here you can see our first observations were featured on the cover of Nature. First, we proved that FRBs can be detected all the way to 400, down to frequencies very low, down to 400 megahertz. That was not certain at the time. It was a bit of a risk, but indeed they are present. You can see all of these de-dispersed waterfall plots for our first 13 fast radio bursts detected with CHIME. That was just the start of the floodgate. This was the number of fast radio bursts as a function of year up until 2019 when we turned on CHIME. You can see the original Lorimer burst detection, and then a few others, mostly with the Parkes Radio Telescope, and then a few from ASCAP, as you can see. And then CHIME turned on. And this is the situation, actually only as is the end of 2019. We've still been collecting data, so we've detected way more. So there's basically CHIME, because of its massive field of view, is able to collect hundreds, in fact now thousands of fast radio bursts, which is the statistics that you need ultimately to be able to make progress on this. And so the sort of progress that we're able to make is we have reported 18 new repeaters. So because we survey the sky every single day, we can find the repeating sources quite easily. This was our first 18 repeaters. We're working on a publication now with many more repeaters. And so we, first of all, proven repetition in the FRB population is not uncommon. We certainly don't see that all FRBs are repeaters, but we keep observing, and every now and again, one that we hadn't seen, turns out it is a repeater. So we're still trying to answer the question of, are they all repeaters? But there's some evidence that actually there's very strong evidence in a publication we just submitted that the repeater bursts have slightly different morphologies. They're a little broader and have slightly different spectral properties. That is, the distribution in radio frequency space is also unusual compared to the non-repeating population. So there's some hints that there are two different classes of objects, but we're really not yet certain of that. CHIME has also allowed us to make some other surprising discoveries about fast radio bursts. In this case, we discovered a fast radio burst with periodic activity, that is, repeats only every 16 days in a few day window. So these plots are a little technical, but the gray regions here, this is now time where we're going from September 2018 till November 2019. The red arrows are where we detect bursts from this repeating source. And they're always in these little gray lines, even though we have exposure, and that's what this black line shows. This is where we see the region on the sky every single day, but we only seem to detect the source every 16 days. Why every 16 days? We're really not sure. Perhaps the source is in a binary system. Perhaps it's a precessing source. There's lots of models to try and explain this periodicity. But the bottom line is we're still not sure. And are all repeating fast radio bursts periodic? We don't yet know. That source was so prolific and now predictable, we could get an interferometric localization with it. So it is the second repeating fast radio burst for which we have localized it. And it is on the outskirts of a large spiral galaxy. So it seems like the first Arecibo repeater might have been a bit of an anomaly in the end. It's sort of funny when the first source is an anomaly, it leads you down strange paths. But nevertheless, we've recently got Hubble Space Telescope imaging of this periodic repeater, and we find it's just outside of a star formation region, which is interesting. We might have thought if it was a magnetar or a very young neutron star, that it might be in a star forming region, but no, it's just outside, which is curious. We also recently detected, using the CHIME telescope, a galactic magnetar, which earlier I told you magnetars in the galaxy aren't known to produce giant radio bursts. Well, one did. And perhaps the reason that they weren't known to produce giant radio bursts is because we didn't have large area radio detectors to detect those bursts. But in April last year, just after the pandemic started, the telescope continued to function nominally. It has no moving parts. It operates, and we can all log in remotely from our living rooms at home, staying safe from the pandemic, but also getting great science done. And here was a double burst from a galactic magnetar at the same time as an X-ray burst detected here with the European Integral mission. So that was really exciting, and it suggests this is one of the reasons we think magnetars are a leading model for fast radio bursts. Now, could all FRBs be magnetars? This is a bit of a technical plot just for the aficionados in the audience. We have logarithmically distance on the x-axis and brightness on the y-axis. These are just conventional radio pulsars, and here are fast radio bursts that we think are at very large distances. These are all galactic sources. The radio pulsars are galactic sources, FRBs are extragalactic. And you can see the brightness of the galactic magnetar that we discovered was way, way up here. But of course, it's quite nearby. So you have to convert everything to energy, which is what these horizontal lines are. And what you can see is that the energetics involved with this galactic magnetar burst falls short of explaining the energetics of fast radio bursts, including especially the most distant ones, which are many orders of magnitude more luminous. But nevertheless, it bridged a massive gap and suggests that, well, maybe there's super powerful magnetars out there that could be FRBs, but we still don't know. So coming soon, just to wrap up, we've submitted our first CHIME FRB catalog containing 535 sources, along with in-depth analysis of many different properties I don't have time to describe. We will be providing public alerts to the astrophysical community in near real time. Anybody will be able to follow up at fast radio bursts. We're still getting the kinks out of that system. And finally, we're embarking on construction of CHIME FRB outrigger telescopes to be located around North America that will allow us to do interferometry on every CHIME FRB detected event in near real time, quasi real time, so that we will be able to sky localize every FRB that CHIME detects and find the host galaxies. Our goal is to identify host galaxies for over 1,000 fast radio bursts using CHIME FRB outriggers. So that's what I had to tell you about today. You can see all of the institutions that are involved. I hope that's not cut off, but we have University of British Columbia, McGill University, University of Toronto, the National Research Council, and some other partner institutions that are helping out. Here's our wonderful team. This is a huge team effort. I'm so privileged to work with these gifted students, postdocs, and of course, my faculty colleagues on this project. It is an honor to be working with them, as well as with our project office and project manager. It's just a wonderful team. And here you can see our funding agencies from Canada Foundation for Innovation and the Gordon and Betty Moore Foundation more recently. And I will thank you very much again for your attention. I'll be happy to answer any questions in real time.
Vicky, thank you very much for a super talk, really showing how to be able to reach out to a wide audience. That was really very excellent and very stimulating. So thank you for that. And let me just welcome everyone to this Q&A. Remind you that you can submit questions for those of you who haven't already on Slido. And it's a disappointment we're not actually able to do this in the Royal Society, as I mentioned at the beginning. But it's great that we can connect with people across the world for this Q&A. So you're all very welcome. So we've got a bunch of questions here, Vicky, and they're actually, there's sort of a vote that takes place, as I'm sure you know, on Slido for some of the most popular ones. But I'm actually going to exercise some executive authority and ask a question that's not necessarily at the top. But it's really, I guess, what's the significance of the understanding of these things? What does it tell us, perhaps, about the broader nature of the universe? Can we learn something, big picture about what the nature of the universe is from all of this?
Oh, that's a wonderful question. First of all, whenever nature shows us that it's capable of, extreme luminosities, tremendous energies, huge explosions, there's physics there that, it's unclear how it happens. So right away, there's how does nature pack such a punch? But in the case of fast radio bursts, there's another reason that they're quite interesting, and that's because they serve as novel probes, novel little flashes of light that have encoded in them a lot of information about their propagation, about the plasma between the source and the Earth, meaning that we can learn about the structure of the universe by studying large numbers of fast radio bursts. We can learn about not just the free electron density, but its distribution. We expect galaxies have halos of free electrons, and so we don't really know the sizes or how many free electrons there are. But along the way, these fast radio bursts encounter many galactic halos. So you can study the large scale structure of the universe in a really new kind of way. So they're both new cosmic probes, but also intrinsically they're quite mysterious and powerful.
Okay, thank you. So I'm going to go to one or two of the sort of popularly voted questions, and the one that's received the most votes is the following. Most of this relies on the assumption that the source is a burst. Can the source, being a sweep, be truly ruled out?
Can the source, being a sweep, be, so in other words, that it's that it's emitted as a 1/f², as a 1 over frequency.
The issue is it's not a sort of instantaneous process across the frequency spectrum, but it's actually sort of coming out at slightly different times.
Right. So there's a whole, so that's a great question. I love that question because, think out of the box. Why does it have to be a sweep? So number one, this dispersion of radio waves through free electrons is ubiquitously observed within our own galaxy. And I didn't take the time to say that, but we know of thousands of galactic neutron stars, which we call, that emit regular radio bursts. We call them radio pulsars. And every one of those bursts is always swept to a degree that exactly depends on distance in the way I described. And we know that with certainty because for many of those sources, we have independent estimates of their distance or independent measurements of their distance through a whole variety of techniques, either by the parallax method for those who know what that is, or by association with another object, either another star, something that so where we know the distance to that other object. So knowing the distance and seeing the sweep and realizing, oh, the sweep is always, roughly speaking, up to some variation proportional to that distance, then you know that sweep has to be due to the propagation of the source. That said, so that's reason number one that we don't think it can be swept out the source. Number two is that we exactly as we inferred from those sweeps, indeed they are then coincident with galaxies. And you might say, wow, who says that that's a real coincidence? But you can calculate the probabilities. We know the density of galaxies on the sky. We know in any one region of the sky how many galaxies should be there. And when you have an interferometric localization of a fast radio burst, the uncertainty region on the sky is quite small. And so the chance probability, the probability of there just happening to be a galaxy there at the sort of distance that you infer from that sweep, well, it's too great a coincidence. It's impossible. And then you see it over and over again. So is it possible that a tiny fraction of the sweep is intrinsic to the source? That we could not rule out. Indeed, we could not rule out, but it cannot be dominated by the source. It has to be dominated by the propagation effect as described.
Thanks, Vicky. So the next question, is it possible that FRBs can echo, for example, by bouncing off other objects in space?
Yes, so there are definitely models where, for example, there's models in which they can be gravitationally lensed. So the echoing, in a way we do observe, so there's different ways you can interpret that question. One is that, the radio waves really are hit something else and get scattered back into our line of sight. And indeed, we do observe that, a scattering phenomenon, although it's not over it's not off of a single object. It's off of, the way I describe the dispersion is that I suggested to you that the electrons doing the dispersing are uniformly distributed between you and the source, which is not necessarily true. Just what I said earlier about galaxies having free electron halos implies that it's not uniformly distributed. And indeed, when you have lots of clumps on relevant size scales, you can have multiple scattering of the radio waves. And we observe in many fast radio bursts, which probably some of the ones I flashed in front of you had this beautiful scattering tail, where the radio waves have clearly bounced off something. Radio waves that would have gone elsewhere get scattered back to our line of sight, and so are slightly delayed. And we see these beautiful tails on some of the bursts due to scattering. So that's one form. Otherwise, gravitational lensing, which is not exactly a bounce, it's more of a due to gravity, the light can be bent back into our line of sight. That is predicted to to be possible and to be observable for fast radio bursts, but not very common. So the sorts of numbers you predict are, you'd have to observe 10,000 of these to see 1 or 2 lensing events. And so we haven't yet collected enough where you could rule that out or detect one.
Okay, that's great. You've actually answered another question, which was, have any FRBs been detected that have been gravitationally lensed? So I think you've kind of answered that one. So let me ask another one, which is, what does one have to do to convert an observing tool to observe FRBs? What sort of modifications do you have to make?
Right. And this is of course a very relevant question, because CHIME, the radio telescope, was designed for a totally different purpose. They were looking at, and still are, in fact, the 2 experiments happen at the same time, because you can split the radio signals. But they were looking at hydrogen gas, which produces a line at 1.4 gigahertz or 21 centimeters. But at cosmological distances, because of the expansion of the universe, that line is redshifted into the 400 to 800 megahertz band. And that's how that radio frequency range was selected, specifically to target specific redshift range where the expansion of the universe starts to accelerate. So it's very interesting cosmology to do there. But for that experiment, nobody cares about time resolution. What they're going to measure doesn't change on a time scale of a millisecond. So what has to change is that you have to be able to read out the data much, much faster. So you need much higher cadence, but also you need higher frequency resolution. And that is because because of the dispersion problem, if you are detecting over the full band at once, or even over, chunks of the band, of the radio band, your signal's dispersed. The signal gets spread out, and that can wash out the burst. So if you want to maintain good sensitivity to short duration dispersed bursts, then you need both high time and high frequency resolution, which means very high data rates and very fast computers. So we had to add, the original CHIME telescope cost about $12 million to build. We had to add something like another $6 million just for the computing to enable all that digital signal processing.
Okay, great. And last question, because we're sort of running out of time. Can the FRBs be from a double star, one a neutron and then one other star, where the neutron star is taking mass off the other star? reaching a critical mass energy, and for all intents and purposes, then you get a burp which ejects the extra mass energy.
Well, okay, so what's being described here is an accreting neutron star binary. And by the way, for other listeners, we know of many of those in our galaxy and in external galaxies as well, because it turns out when the material falls onto the neutron star, they're very bright. The material gets very hot and emits copious X-rays. Now, in terms of fast radio bursts, certainly if there was something in the accretion of that matter onto the neutron star that could produce a burst, like, so for example, in these X-ray binaries that I just described, we do see X-ray bursts, and that has to do with material igniting thermonuclear explosions on the surfaces of the neutron stars. That's observed also, quite commonly by X-ray telescopes. Now, those are not typically accompanied by radio bursts. So you'd have to find some reason either why we've missed those, which could be for the same reason we've been missing Magnetar radio bursts, because we just didn't have the telescopes with the wide area field of view. But you'd also have to, come up with some mechanism for producing those radio waves. I mean, that said, we know in an isolated neutron star, like I described, the radio pulsars we see ubiquitously in our galaxy, they produce radio bursts. We know this, we've seen it, just not anywhere near the luminosity. So what about the accreting binary would suddenly get you the 9 orders of magnitude you're missing in luminosity? I'm not sure. But, what you described, there's probably, sufficient energy there. I can't think of a reason to rule that out, but then you have to explain why radio waves. And if there's all this material falling in, sometimes radio waves have a hard time escaping very dense regions. The optical depth is to radio waves very high. I don't know.
Okay, that sounds like a conversation for a longer time, maybe
yes,
another time.
Definitely.
Thanks very much. So again, Vicky, thanks for a great talk. Congratulations again on receiving the Bakerian Award. And I'd like to thank everyone who's joined us for this evening's lecture, if it's evening for you, wherever you are, and for some great questions. And we look forward to joining you again at another time as an audience for a further Royal Society award. Thanks very much. Bye, everyone.